Okay, Arno. Hope you're doing good. So we are starting with isotopes, right? I want you to take down the definition that is written on the screen, right? It's a simple concept. What are isotopes? Same atomic number, but different mass number. Okay.
Okay.
Now, you already know that atomic number is the number of protons in the nucleus, correct?
Yeah.
And mass number is the number of protons plus neutrons,
Yeah.
correct? Now, when it comes to the isotopes, right, if you look at this, so either you can say electrons or protons, that it can work that way, but generally what happens, electrons, they can go out of the orbits and they can form ions, right? So
hmm
that's the reason the preferable term is protons. Okay.
Okay.
So now when you have carbon 12 6, carbon 13 6, carbon 14 6, so there are, so these are the three isotopes of carbon. Okay.
Okay.
The proton number is 6, that is the atomic number, right?
Yeah.
If you see over here, right? And the atomic number, right, is 12. Mass number is 12, my bad,
Yeah.
correct? So the difference of this is giving you the neutron number,
Okay.
correct? So how
Yeah.
do we get the neutron number? Neutron number is the, so how do we get the neutron number? Neutron
It's
number is the atomic mass number minus the proton number.
yeah.
So if you notice, the differences is the neutron number.
Yeah.
So they have same atomic number, different mass number. But why the mass number is different? Because each and every isotope has a different neutron number.
Okay.
Correct?
Yeah.
Any doubt with that?
No, all good.
Right? So so the neutron number is 678, right? Now, carbon 12 is omnipresent. Okay, it's widely present all over the earth,
Yeah.
right? Carbon 13 is used to identify the structures. Okay, so basically, if there is an organic compound, we want to know what structure of that organic compound is. We can use carbon 13.
Okay.
Okay, carbon 14, because it has some unique properties and you will learn that at higher level. So I've just mentioned that it can be used to identify the structure. Carbon 14 is used for carbon dating, meaning if you get a fossil which is, and they say that this fossil was 300 years old, right?
hmm
How do they know it? That is because of the presence of carbon 14,
Okay.
which is a radioisotope.
Okay.
Okay, so carbon dating and it is radioactive. So can you take down these points?
Yeah.
Done.
Yeah. Done.
Okay. Have you copied this? Neutrons are
Yeah.
different. Okay. Now, what is radioactive? So, ability of an atom to emit radiations, right?
Okay. Yeah.
So, there are certain atoms which are able to emit these particles. There are two particles, that is alpha particle and beta particle. Okay. And there is
Okay.
gamma rays. Okay.
Yeah.
So, alpha particles, the mass is 4, charge is plus 2. Okay.
Okay.
It has the least penetrating power. Like it can be stopped by a paper.
Okay.
Okay. Beta particle is the mass is it's negligible. It's similar to that of electrons, you can consider.
Okay.
Okay. And has a negative charge, and the uh, penetration power is low. Why the penetration? Like it can be stopped by wood.
Okay.
Okay. Gamma rays are are rays, so there is no mass, there is no charge, right? Because these are
Yeah.
rays, they travel by the speed of light,
Okay.
and penetration power is extremely strong. Like it is
Okay.
stopped by metal, like a metal block is required to stop it.
Okay.
Okay.
Okay. Done.
Then you should remember this term, that is transuranic, after uranium. So everything is transuranic, and these are generally radioactive. Okay.
Okay.
So uranium 238 and 92, right? If it emits an alpha particle, right? So if it emits an alpha particle, it will form X234 and atomic number of 90. So because it is releasing like because it's releasing an alpha particle, the mass number is reduced by 2 and the atomic number is reduced by 2. Sorry,
Okay.
mass number is reduced by 4 and atomic number is reduced by 2. So you get a new element. You said that after decaying, you get a new element, right? So
Yeah.
that new element is having a atomic number of 90. And if you compare that on the periodic table, you will see that it is thorium.
Okay.
Okay. So what I want to emphasize is, if an alpha particle is emitted from the uranium, the exact mass is getting reduced. The
Hmm.
exact atomic number is getting reduced. But if a beta particle is emitted, right, the mass number is not impacted because it has zero mass.
Yeah.
But if you see -1, right? So what happens? The atomic number increases by 1.
Okay.
Okay. So instead, if let us say here, just this is a hypothetical example. Okay. If a beta particle is emitted, right? So beta is what? 0 minus 1, correct?
Yeah.
So you will get X, that is 238, but instead of 92, you will get 93.
Okay. Got it.
Make sense?
Yeah.
Okay. So this, I don't know whether it is covered for you in the school or not, but if it is not covered, it's a good general information.
Yeah.
Okay, then you can use for isotopic abundance. This is the formula that I generally give to my students. Okay, where I ask them to write down average atomic mass is equal to I1 P1 plus I2 P2 plus I3 P3 and so on till IN Pn, divided by P1 plus P2 plus P3 plus P4 plus Pn, where P stands for the percentage, I stands for the mass of the isotope.
Okay.
Okay. Now, if you have a habit of expressing the percentage as in decimals, okay,
Hmm.
then you don't need the denominator,
Okay.
right? Let us say if something is 50%, so I have seen students taking it as zero point 0.5,
Yeah.
correct? So then you don't need the denominator.
Okay.
Okay, but if you take 50, then you need the denominator.
Okay.
Am I clear?
Yeah.
Okay, can you solve this?
Yeah. One second. I'm just writing down the formula.
Yeah. Any difficulty in the formula?
No, no, just writing it down.
Is the formula different than what is given in the school?
No, no.
Okay,
Okay, yeah, got it.
done. Can you solve this question now?
Yeah, it's 35.5.
Yeah, that's correct. Okay, so this is the way I solve it. 35, 75, 35, 25, 75 plus 25, 35.5. That is the average atomic mass. Okay, now if you compare this with the one on the periodic table, you will notice that it is 35.45.
Yeah,
Yeah, that's because of the decimals that I've chosen over here, the percentage that I've chosen over
okay,
here. Okay, sorry, I said decimal. That is a percentage. I think it is 74 point something and 25 point something. So you have a difference in the number. Okay,
okay,
so that's done. So the other way is you can call it as x, 1 minus x. So let us say if you know the average atomic mass, you can determine the oh, you can determine the percentage,
okay,
right? So how do we do that? We take the percentage as x and 1 minus x will be the other one, right? And if
yeah,
we solve the equation, you will get 75 and 25.
okay, got it.
So can you write down this?
Yeah,
It works when you have only one isotope unknown. Okay.
okay, yeah, okay, got it.
Mm, okay, so that's about the isotopes radioactivity. Now tell me what next.
Next is uh, periodic table, like trends, etc.
Trends. Okay, so for the trends, let us start with ionization energy. Okay,
Okay.
so as on the screen you can see, I have written ionization energy, right?
Mm-hmm.
And I have written that there is an atom. From that atom, you remove an electron, right? If you
Yeah,
remove the electron, you convert that atom into a cation.
yeah,
Okay, so ionization energy is the energy required to remove this electron. Okay,
yeah,
to remove the electron. Okay, from a gaseous atom. Okay,
okay,
so let it be any atom. If there is a neutral atom, If you remove the electron from it, you are forcefully removing the electron, then you are actually determining the ionization energy.
Okay.
Make sense? Simple.
Yeah.
And because in a particular atom, the number of protons and the number of electrons are equal, correct?
Yeah.
Hence, your cations are always positively charged,
Okay. Got it.
right? Because in cations, the number of protons is greater than the number of electrons.
Okay.
Okay.
Yeah. Okay. Got it.
Then there is a concept which is first ionization energy, second ionization energy, third ionization energy. Okay.
Yeah.
So first ionization energy means when only one electron is removed from a neutral atom.
Okay.
Second ionization energy is when you're removing second electron from the positive cation.
Okay.
Okay. Third ionization energy is when a doubly positive cation, from that you remove an electron. So you get a x plus 3,
Okay.
right?
Yeah.
So the concept is it is relatively easy to remove an electron from neutral, correct?
Yeah.
But if something is positive, right, from that you are trying to remove an electron, it is difficult.
Yeah.
Further, doubly positive, from that you are trying to remove an electron, further difficult.
Yeah.
So the trend between first ionization, second ionization, and third ionization is generally first ionization energy is smaller than second, which is smaller than the third ionization energy.
Okay.
Okay.
Okay. Got it.
Okay. Are there more questions given to you from the school regarding the isotopes, like at average atomic mass that you want to do?
No, not really.
Okay, then
No.
fine. So here's the concept.
We just started it today. So
Okay.
we haven't like our class goes slow, so they haven't fully covered it yet.
Okay, no problem. So from my side, I have told you the formula. I have taken one representative example. Okay.
Yeah.
But if you want to do more examples, we'll do that. Okay.
Yeah, yeah.
Yeah. So this part is clear. Ionization energy by definition is clear.
Yeah.
So you have a neutral atom. You remove an electron, you convert it to a cation.
Yeah.
Correct? Now
Yes.
there is a problem that the student face. When I say atom, they get confused between metals and non-metals.
Right.
Right? For the definition, it doesn't matter whether it is a metal or non-metal.
Okay.
If it is a metal or a non-metal, doesn't matter. When we talk about ionization energy, we are converting it to a cation.
Okay.
Correct?
Yeah.
Now comes the next concept. For a metal, is it easy to remove the electron?
Yes.
Why?
Because metals want to give away electrons.
That's right. They want to give and you're trying to remove. So it is easy.
Yeah.
Correct? Non-metals, on the other hand,
They want to take electrons.
and you're forcing the electrons away from it. What they will
Yeah.
do?
They will pull harder.
They will resist. So you will require more force. Correct?
Yeah.
So ionization energy of the non-metals is always higher than that of the metals.
Yeah. Okay.
Okay, this is one way to remember it. Clear? Any doubt?
No. All good.
Okay, so that is one. Now let us, we spoke about this metal, non-metal. So what I told you, if it is a metal, right, it
Yeah.
wants to lose electron. Correct?
Yeah.
Non-metal wants to gain electron. Correct?
Yeah.
Natural tendency. So, ionization energy of metals, when we talk about ionization energy of metal, is lower than that of non-metal. Correct?
Yeah.
Any doubt?
No. Good.
Okay. So, I spoke about this. Then let us talk about next, that is electron affinity.
Okay.
Okay. What is electron affinity now? You have an atom, you add an electron to it, you convert it to an anion. So you are forcefully adding an electron to the atom. You are not looking whether it is a metal or a non-metal.
Okay.
Correct?
Yeah.
So what is electron affinity? It is the energy change when electron is added.
Okay. Energy change when electrons are in.
So that energy can be more or the energy can be less.
Yeah.
Okay. So when we say energy is more or energy is less, that means we are talking about stability and instability. So basically, when you are adding an electron to an element, and if it is becoming unstable, that means the energy is increasing.
Okay.
Okay. And if you have an element, if you add an electron to it and it is becoming stable, that means the energy is decreasing.
Okay. So if uh
So if I take an example, let us say Z is the number. If you add an electron and the energy is increasing, right? So let us
yeah.
say it becomes Z1. And other concept is when you add an electron, it becomes Z2, right? So
Yeah.
delta E, that is change in energy, is Z1 minus Z, right? So delta E1, delta E2 is Z2 minus Z. Let us say
Okay.
this is 100, this is 120, and this is 80,
Yeah.
right? So I said a scenario where when the electron is added, energy increases 120, and another scenario where energy is decreasing Z2. So in
Yeah.
this case, the energy would be plus 20.
Okay.
Or in this case, the
Yeah.
energy would be minus 20.
Yeah. Okay.
Correct? So that means when it is negative, it is more stable,
Okay.
right? So the element is readily accepting the electron. But if the
Okay.
value is positive, that means the electron is not getting easily added. We are forcefully adding the electron.
Okay.
And which scenario? Let us now consider metals and non-metals. Who will take the electrons readily?
Non-metals.
So non-metals generally will have a electron affinity that is negative.
Okay.
Okay. Metals on the other hand will have electron affinity which is positive.
Okay.
We'll talk about the trend, don't worry. I'm just trying to give you a general idea about the electron affinity and ionization energy. Okay.
Okay.
Any difficulty till here?
No, all good.
Can you copy all this?
Yeah.
Okay.
Okay.
Done. Everything has been copied.
Yeah.
Okay. Now, for the sake of understanding, always I want you to remember this concept. I am repeating it. I'm repeating myself, but the reason I'm repeating is because I don't want you to have that doubt in future. Ionization energy means forcefully removing electron.
Yeah.
Electron affinity means forcefully adding electron.
Okay. Yeah.
Clear? You are converting an atom to a cation in ionization energy. You are converting an atom to an anion in electron affinity. Correct?
Okay. Yeah.
Any doubt?
No. Good.
Okay. Now let me go to the next concept, that is the atomic radius. And for that, I'll go to the textbook because I've seen a very good representation so that I can explain you uh, the the trend or what is atomic radius and atomic size and all that. Okay, so let me load that. Any doubt about electron affinity, electron ionization energy?
No. All good.
All good, right? Okay, good. Okay, now here we go. So you're aware about the octet rule and all that stuff, right?
Sorry.
You are aware about the octet rule, duplet rule.
No. No. We didn't.
Okay, you don't
No.
know about octet rule. The like you mentioned that metals have a tendency to lose electron.
Yeah.
Why do they lose electron?
Um, I believe it's because it's easier to, um, like, for example, sodium has only one valence electron. It's
Correct?
easier to lose one than gain seven.
Why it has to lose one? That is what I'm coming to. So
Because what do you call it? If it has a full valence shell, it is stable.
yes, so what is that full valence shell? You're right. Whatever you said is absolutely right.
Yeah.
Okay, but what is that full valence shell?
The outermost shell of an atom.
Okay, now let us come to this sodium. Can you see?
Yeah.
Right? Can you see sodium has three levels of energy?
Yeah.
One, two, and three. Right?
Yeah.
If you notice, the closest orbit has only two electrons.
Yeah.
Right? Then the outer of that has eight electrons.
Yeah.
Right? Sodium in all has 11 electrons. So that one electron is remaining in the third orbit.
Okay. Yeah.
Right? If it if it removes this one electron, so I'll write it as 281. Correct?
Yeah.
If it loses that electron, it has a stable electronic configuration, meaning it has
Yeah.
that octet. So 8 means octet.
Okay.
Okay. So each and every element tries to complete the octet.
Okay.
Okay.
What?
You might have heard that chlorine accepts one electron.
Yeah.
So it is 287. Correct?
Yeah.
See, 2, 8, and 7. If we calculate, or sorry, here 2, 8, and 7. Here it is only 1. So, and others are in pair, right? So, if we add
Yeah.
one electron, it becomes 288. Because it is gaining that magic number 8, the octet rule, it is becoming stable,
Okay. Got it.
right?
Yeah.
So, what is octet rule? Any element, if it has its outermost element or outermost shell with 8 electrons, it is more stable.
Yeah. Okay.
Okay, and each and every element tries to have those 8 electrons in its outermost orbit,
Okay. Yeah.
right?
Yeah.
Exception to the octet rule is hydrogen and helium.
Right. Because they only have one shell.
Yes, and if it is the first shell which has only 2 electrons, so hydrogen is satisfied if it is having 2 electrons. Helium
Okay.
always has 2 electrons.
Yeah.
Okay,
Okay.
right?
Yeah.
So we spoke about octet rule,
Yeah.
right? Now let us understand the periodic table here. Okay, so when we talk about periodic table, we know that there are group numbers. Periodic
Yeah.
table has group numbers, and it has period numbers. Okay, so can you see the group numbers over here?
Yeah.
Okay, these group numbers are extremely essential because the group numbers help us determine the valence electrons,
Okay.
right? Because these belong to the first, they have one valence electron. These belong to the second, they have two valence electron. Transition we ignore, we go to 13 to. So 13 means 3 valence electrons. 14 means 4 valence electrons. 15 means 5 valence electron. 16 means 6 valence electron. 17 means 7 valence electron. 18 means 8 valence electrons.
Yeah. Okay.
You are aware of this, right?
Yeah.
Good. So hydrogen and helium. Helium ideally should have been over here
Right. Yeah.
because it's an S block element. But it has been put along with all the noble gases
Yeah. Okay.
be- because their characteristics or their properties are similar to that of the noble gases.
Okay.
Okay, but it is a S block element.
Okay. Got it.
Okay, then what else I have to tell you? That first is the alkali metals, second is the alkali earth metals. Then these bottom of the periodic tables are the lanthanides and the actinides. After lanthanum are all the lanthanides. After actinum, all are actinides.
Okay.
Okay, can you see this line over here? Zigzag
Yeah. Those are what do you call it?
metalloids.
Yeah, metalloids.
From the either side, they are the metalloids. Can you see the
Yeah.
one here which are green?
Yeah.
Those are the halogens.
Right. Okay.
Out of these, the astatine is radioactive.
Okay.
Okay,
Okay.
any doubt?
No. 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 All good.
All good. Okay. Actinides, actinides, I'm done. Uh, then what else? And left hand side of the periodic table, group 1 and 2 are the metals. 13 and 14 are metalloids, right?
Yeah.
Generally, I told you the one goes between the across the line boron, aluminum, silicon, germanium, arsenic, tin, tellurium, polonium, I believe, right?
Yeah.
So these are all metalloids which are across this line. Okay,
Okay.
and from 14 to 18, these are all non-metals.
Yeah.
Okay,
Okay.
no mission metals. Okay, that's done. So zigzag the elements right next to this line on either side. It are metalloids, right?
Yeah.
That is done. Okay, so I told you about the groups. Other important part that you should know is periods. One, two, three, 4, 5, 6, and 7. So there are 18 groups,
Right.
7 periods,
Okay.
right? Or 18 columns, 7 rows.
Yeah. Okay.
Okay, and there are 2 rows at the bottom of the periodic table which are lanthanides and actinides.
Yeah. Okay.
Okay, any doubt till here?
No. All good.
Oh, good. Okay, now let us understand this. So if you look at the periodic table, okay, if you look at the first period, second period, third period, what do you notice? The number of shells.
They increase by one.
They increase by one. So as you start from top to bottom in the periodic table, what will happen? The shells are increasing.
Yeah, okay.
And if the shells are increasing, what will happen to the size?
They will also increase.
Right. So as you go top to bottom in the periodic table, atomic size increases.
Okay, got it.
Easy.
Yeah,
So how will you remember that the size is increasing?
as you go top to bottom, shells, there are more shells, so they get bigger.
Yes. And what is the definition of atomic size or atomic radius? Center of the nucleus to the outermost electron.
Okay,
So distance is measured from the center of the nucleus to the outermost electron.
okay,
And
got
if
it.
there are more shells, by default, the size will be larger. So atomic
Okay,
radius will be larger.
okay,
Okay. So atomic radius, can you write down this?
yeah, okay, done.
Okay. Now there is another concept that is uh, one is atomic radius, other is bond length. Okay. So if you see
Okay.
hydrogen over here, when hydrogen is actually a like, have you heard of Hofbrinkel?
No, wait.
Okay. Okay. So Hofbrinkel are the gases on the periodic table which are actually diatomic.
Okay,
HOF, Hof, hydrogen, oxygen, fluorine,
okay,
Brinkel, bromine, iodine, nitrogen, chlorine.
okay, okay, got it.
Okay, so it is Hofbrinkel. It's better you make a note of it somewhere.
Okay,
So they naturally exist as diatomic molecules.
okay, got it.
Yeah. Then
Yeah,
so I wanted to talk about bond length. So it is distance between the two nucleus
okay,
when we talk about a bond length in a molecule. Okay. So pay attention over here. Now we are talking about the trends of the atomic size. As you go down the periodic table, the atomic size is increasing.
okay,
Why?
because they have more shells.
Right. Now let me take example of the third period. That is so. Okay. Now let me take the example of the third period over here. Right.
Yeah,
And we'll try to go left to right in the periodic table. If you notice, there is a decrease in the size. Right.
yeah,
So as you go left to right in the periodic table, the size is decreasing. Correct.
yeah,
Right. Okay, now let us understand the reason for that. So they belong to the same period, so it has three shells,
yeah,
correct? Now let us talk about the number of protons, and so we have so Okay. Okay. So let us talk
Yeah.
about the number of protons, right? So number of protons are how much? 11, 12, 13, 14, 15, 16, 17, 18. Correct?
Right.
Now
Yeah.
let us talk about valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Correct?
Yeah.
And then let us talk about the difference between them. So what is the difference? 10, these are innermost electrons.
Right.
Okay, or these are called as shielding electrons. So each of them are having 10 shielding electrons. Correct?
Okay. Yeah.
So you have 11 protons and 10 shielding electrons. Okay,
Okay.
you have 12 protons and 10 shielding electrons. You have 13 protons and 10 shielding electrons. 14 protons, 10 shielding electrons. So what is happening as you go from left to right in the periodic table? The central force is increasing. What is
Right.
central force? Attractive force.
Yeah.
As you go left to right, the attractive force is increasing, but the shielding force is remaining
Shooting.
constant.
Right. Okay.
Correct? So because
Yeah.
the shielding force is remaining constant, what is happening? The electrons are coming closer to the nucleus,
Okay.
and hence
Got-
the size is decreasing gradually.
Okay.
Okay,
Okay.
is it easy to imagine?
Yeah. Yeah.
Okay, can you write this down?
Yeah.
So remember, the inner orbit electrons are called as shielding electrons.
Okay. Okay. Done.
Yeah. So what happens as you go top to bottom in the periodic table to the atomic size?
Atomic radius increases.
As you go left to right,
Left to right decreases.
decreases. As you go right to left,
Increases.
yeah. But I have a tendency of saying top to bottom and left to right. Okay.
Okay.
So, and I told you about effective nuclear charge. Well, now, can you write this down? What is effective nuclear charge?
Yeah.
I told you the difference between the shielding and the protons.
Yeah.
Correct? So, can you write down that the net force experienced by an electron in an atom due to the positively charged nucleus? And I explained you in terms of difference between the protons and the shielding electrons.
Okay.
Now, next is ionic radius. Okay, can you write down? is a measurement of the size of an ion, usually expressed in picometers, the distance from the center of an ion to the outermost electron. Same concept.
Okay.
But here, earlier it was an atom, here it is an ion.
Okay.
Okay, so you copied that. Okay, now
Yeah.
let me explain you this part. So if you see sodium atom, it has 190 picometer as the size, but
Yeah.
a ion has a size of 95. Whereas
Right.
chlorine atom has a size of 79, but the chlorine ion has a size of 181. So the logic is if there is a cation that is smaller than the atom, if there is an anion that is larger than the atom.
Okay.
Okay, right?
Yeah.
And now let us understand the reason for it. Any doubt till here?
No, no, all good.
Good, right? Okay, so let me see if I have the notes for it or I'll write it on the screen. Okay, so it's better I write it on the screen. Okay, so we understood so far that sodium has three orbits, three shells. Chlorine
Yeah.
also has three shells. So if I consider the nucleus, there are three shells, one, two, and three. Correct?
Yeah.
So this is sodium. Chlorine also has three shells, nucleus, one, two, and three. I have drawn the nucleus pretty big. The nucleus is like extremely tiny. Okay.
Right.
This is
Yeah.
just for the sake of representation, but remember the size of the nucleus is very very small.
Okay.
Okay, compared to the size of the atom. Okay, so now when
Okay.
we talk about this, the electronic configuration is 281, correct?
Yeah.
And when we talk about sodium cation, it loses one electron, right? So electronic
Right.
configuration is 2 and 8. So you have the nucleus, you have one shell, and you have the second shell,
Right.
correct? So that means one shell is completely lost.
Right. Yeah.
So the cation size is generally smaller than the atom.
Okay.
Another reason is the electrons are 10 in a cation.
Yeah.
There are 11 protons. So you have more protons than the electrons. That means the central force is larger than the number of electrons.
Yeah. Okay.
That is also another reason that the size is smaller.
Okay. Got it.
Correct? Easy.
Yeah.
Now you
Easy.
have 287, right?
Yeah.
When you have chlorine anion, it is 288. Okay.
Okay.
Now already the shell is crowded here, right?
Right. Yeah.
When you have that extra electron, it becomes overcrowded.
Okay.
Because it is becoming overcrowded, the electrons start repelling each other and the size bulges.
Okay.
Correct?
That makes sense because similar charges. Yeah.
Yes. Another concept, number of protons 17. Number of electrons are 18. So the central force is also weaker
Right.
in front of the number of electrons.
Right. Yeah.
So the size of the anion is generally larger than that of the atom.
Okay. Got it.
Easy?
Yeah. Easy.
Can you write down this?
Yeah. Okay. Done.
Done. Okay, that's great. We discussed ionization energy, right? So this part is clear. Size of the cation is always smaller than
La.
that of the
Yeah.
atom. That of the anion is larger than the atom. And
Yeah.
when it comes to the ionic radius, the same concept. As you go down the group for the ions, size increases.
Right. Okay.
Okay,
Okay.
but left to right, it should increase because you're moving from a cation to anion. But
Okay.
generally, they don't ask about that. They always the comparison is between the metal and the non-metal.
Okay.
Sorry, the metal and the cation, non-metal and the anion.
Okay.
Okay,
Got it.
but always remember when it is a non-metal, it will be an anion. So anion will be larger.
Okay.
So if there is a comparison between cation and the anion, always try to have anion has the upper edge. Okay.
Okay.
Mm, ionization energy, electron affinity. We discussed all this. Okay. Now let us talk about the trend. Okay. So one trend I told you, okay, I told you about both, right? Ionization energy, as you go down the group, it increases. Sorry, what happens to the ionization energy? Did we discuss that? No, right?
No.
Okay, now let us understand that now. From this very example over here, check the atomic radius. What is happening to the atomic radius?
Atomic radius is increasing as we go right to left.
From
And from right to left and top to bottom.
from left to right, it is decreasing.
Yeah.
Yeah, and from top to bottom, it is increasing.
Yeah.
Right? As you go top to bottom, it is increasing, correct? That means the
Yeah.
distance from the nucleus to the outermost electron is increasing,
Yeah.
correct? What do you think? It is easy to remove the electron for cesium or easy to remove an electron for hydrogen?
Easier to remove the thing for cesium
Why?
because it's further away. It's a larger atom.
Because it's a larger atom, it is easy to remove the electron as it is away from the nucleus. And nucleus
Yeah.
is the one which has the attractive force. So you guessed
Yeah.
it right. Easy?
Yeah. Easy. Easy.
Okay. What about as you go left to right?
Left to right, it gets harder
Why?
because the atoms get smaller.
The atoms get smaller. So this is what you need to remember.
Okay.
Okay. Now let us talk about electron affinity. Okay.
Okay.
Check what happens when you are on the left hand side of the periodic table and right hand side of the periodic table.
Left hand side is bigger than right hand side.
Okay. Now at left hand side you have metals.
Yeah.
Right hand side you have non-metals.
Yeah.
So when we talk about electron affinity, the electron affinity goes on increasing as we go, sorry, goes on decreasing as you go, sorry, my bad. Electron affinity is increasing as you go from left to right in the periodic table,
Yeah.
right?
Yeah.
Any doubt?
No, all good.
Okay, so let us talk about the electron affinity over here. Check. So this is what was spoken about the ionization energy. Hydrogen, helium. Left to right increases. Left to right it increases. Left to right it increases. Left to right it increases. Left to right increases. Left to right
Yeah.
increases. Okay. And as you go down, it is decreasing. Okay. The energy change that occurs when an electron is added to a neutral atom in a gaseous state. I told you this. So you are forcing a electron to convert to a anion. Okay. Now
Yeah.
check over here. They have given only why they have given only positive numbers. Are these absolute values?
I believe so.
Yeah. So okay. Now the way it is represented. Yeah. Plus. That means it is an exothermic reaction. Correct?
Yeah.
That is released. That means this chlorine is becoming more stable. Okay.
Yeah.
So these values are all negative. For hydrogen minus, right? Carbon it
Right.
is minus. So that means chlorine, if you see minus 349, chlorine has the largest affinity for the electron.
Okay.
Okay. So they are talking about the energy released here. And I told you the definition has energy change, and actually the definition says energy change. So let us stick to what we say. But for the sake of this example and the explanation over here, they have mentioned this is an exothermic reaction.
Okay.
Okay. So 349 means that much is the energy that is released.
Okay.
Okay. Fluorine is 328. Okay. So if
Okay.
you see, they have higher electron affinity. If you see all the metals, sodium 53, magnesium 0, there it is extremely low. Calcium 2, so electron affinity is low.
Okay.
Okay. So ionization energy and electron affinity, it increases as you go left to right in the periodic table.
Okay. Got it.
Okay. Atomic radius increases as you go top to bottom in the periodic table. Atomic
Okay.
radius decreases as you go left to right or increases as you go right to left.
Okay.
Ionization energy and electron affinity increases as you go from bottom to top.
Okay. Got it.
Okay, I told you ionization energy decreases as you go top to bottom. So electron affinity also decreases as you go top to bottom.
Okay.
Okay, can you draw this particular example or the figure?
You know, we already have this in our book. The
Okay,
teacher talks about already.
okay, great. So I hope you have covered all the trends today. And
Yeah.
what you can do is I'll share some notes with you and questions with you. You try to solve those. Okay.
Okay.
Okay, then let's call it a day, Arnav.
All right. Thank you, sir.
Okay, no problem. Bye.
Bye. See you next week.
Yeah.